Some are still joining, and hopefully they will join us in a few minutes of time. At this time, I welcome all of you, and without taking much time, I would like to request Professor Madhumurthy Garu, who is chairperson of the AP State Council for Higher Education, and at the same time, he is also a professor, HAG scale from NIT Warangal, and a very renowned scholar and researcher, and an academician and a teacher, and an administrator as well. So we will begin our program for these quantum series, covering the AICTE minor degree syllabus. There are about 12 courses. We are starting the first two courses as a combined program. So let's hope we will be able to do these programs successfully. And we have things lined up till March 2026. So, there have been great support from Dr. J.B. Reddy Garu, Dr. L. Venkat Subramaniam Garu, and all. So at this time, to start this and to share a few thoughts, I will request Professor Madhumurthy Garu to take this time.
Thank you, Professor Shubhakar. Good afternoon. It is with immense pleasure and a sense of great optimism that I welcome you all to this inaugural session of the Faculty Development Program on Quantum Technologies. As you are aware, as part of the National Education Policy 1986, which recommended that state level planning and coordination be done through a council. The Andhra Pradesh State Council of Higher Education has been established as the first council in the country. And we call it APSHI, the shortest form. At APSHI, we are deeply committed to drive all educational initiatives in higher education across Andhra Pradesh. And our vision is firmly rooted in Swachh Bharat and Viksit Bharat, as well as Swarnandhra at 2047 initiative of the government of Andhra Pradesh, where we wish to fulfill the aspirations of the youth through education, technical excellence, and entrepreneurship. In alignment with our Honorable Chief Minister's visionary goal of establishing Quantum Valley at Amravati, and our dynamic Honorable Minister for Education promising to create 20 lakh jobs and job opportunities, we at APSHI have prepared a roadmap for training of our youth and preparing them to be ready for the future. The roadmap focuses on some of the cutting-edge technologies, to start with quantum technologies, artificial intelligence and machine learning, robotics, and similar sort of activities. And this faculty program, development program, is a cornerstone in this roadmap. And in this process of rebuilding the state after bifurcation, our ultimate aim is to transform this state of Andhra Pradesh into a vibrant hub of innovation and opportunity. With this in mind, we are trying to come up to train our faculty to be able to handle and train our youngsters in the classrooms, to prepare them for the latest of technologies. And this has been truly an extraordinary and an enthusiastic outcome and response from all the faculty members to participate in this effort of conducting faculty development programs on quantum technologies. We are profoundly grateful for the significant support extended by the National Quantum Mission. We also extend our sincere appreciation to MNIT Jaipur for implementing this crucial training activity for Andhra Pradesh. Under the invaluable assistance of the Ministry of Electronics and Information Technology and other industry partners of IBM, TCS, and others. This program is a testament to our collective effort to handhold in the transformation of Andhra Pradesh into the most happening place for technological development. And I would like to extend my heartfelt thanks to all those who have made this program possible. A special note of thanks to Dr. J.V. Reddy, who is heading the Quantum Technology Cell at BSD, for his handholding, support, guidance. In fact, he has been the philosopher of all our activities on quantum technologies. Thank you, sir. We are also deeply thankful to our industry partners, Dr. L. Venkat Subramaniam, IBM Quantum India leader, and Dr. C.V. Sridhar, Head Quantum Technology Initiatives from TCS, who have been so very kind to be with us all through and supporting us even from developing the curriculum for introduction to the degree program as well as the engineering degree activities. We are also thankful to Dr. Mustafa Rahman, research scientist, IBM Quantum, Risha Goyal from the IBM Quantum again. Your expertise and collaboration are invaluable to us in this effort of ours. My thanks also go to the director of MNIT Jaipur, Professor Narayan Prasad Pradhi, who had readily accepted our proposal to take our faculty through this set of modules to be able to enable them handle the youngsters in training them on quantum technologies. We also thank Professor Vineet Sahula, Chief Investigator of INCT Academy at MNIT Jaipur, for his unwavering support. Of course, Dr. Billy Emmanuel Suvagar was so dynamic to come out with a schedule so readily to fit in all possible aspects, accommodating the times despite his other training implications that he has on hand. Thank you very much, Professor Suvagar, for all the effort. In fact, this program represents a significant leap forward in equipping our faculty with the advanced knowledge and skills necessary to prepare the next generation for the quantum era. Each module of the proposed program Foundations of Quantum Computing and Applications is an intensive 20-day, 40-hour duration program designed to equip all those participants with the knowledge and skills necessary to lead the next wave of technological advancement. Let us seize this opportunity to learn, innovate, and contribute to a future where Andhra Pradesh stands as a beacon to technological advancement. The implementation of this program by MNIT Jaipur with the assistance of the industry leaders, IBM, TCS, and the support of the governmental agencies and the National Quantum Mission, the collaborative spirit that will drive innovation in the country and our state in particular. Thank you, all of you, for being part of this momentous occasion. Let's embrace this opportunity to learn, grow, contribute to a brighter, more innovative future for Andhra Pradesh. Jai Hind. Thank you for the opportunity given to us. Thank you very much.
Thank you. Thank you very much, sir. Thank you for your guidelines and especially the vision with which you have started. And we also remember at this time Chandrababu Naidu Garu, Chief Minister of Andhra Pradesh, for actually pushing all of us for this thing and the Amravati Quantum Valley, and also especially APSCHE to spearhead this big task of training so many people. And as of now, I think I have 1100 names with me, and we are trying to facilitate all of them. And hopefully, we will try to get most of them certified in course one, and subsequently in the next courses. And of course, at this time, we really give a lot of credit for the committee that was there, formed by AP State Council for Higher Education. Madhumurthy Garu has been very instrumental in bringing Dr. JBV Reddy, and he was the chairman of that, and we could come up with these programs. So I will request now Dr. JBV Reddy, who is very instrumental, especially for this AICTE minor degree, and he is one of the brain behind that. And he needs no introduction. He is head of the quantum technology cell in the Department of Science and Technology, a very learned scientist himself, and a researcher as well. And he's worked a lot of work on electrical engineering and especially smart grid side. Very big contribution. But of course, he has adapted himself. I would say he is entangled himself. He will give more of his own insights as I look at. And I will request Dr. JBV Reddy to please share few thoughts. Thank you.
Thank you, Professor Saab. Very good afternoon and warm greetings from Department of Science and Technology on behalf of National Quantum Mission. First of all, I would like to congratulate Professor K. Madhumurthy Garu, Chairman, Andhra Pradesh State Council of Higher Education, for commencing and launching India's biggest faculty development program on quantum technologies. This program are aimed at equipping faculty members across diverse disciplines with cutting-edge knowledge and pedagogical skills in the rapidly evolving field of quantum science and its application. And also Professor N.P. Padi, Director, MNIT Jaipur, and his team for running this FDP program. Distinguished members from FSHE, MNIT, IIT Madras, IBM, TCS, MIT, and faculty members and researchers, all our partners who have made this bold initiative possible. It is a great honor and privilege to join this faculty development program on quantum technologies. India's National Quantum Mission is a visionary initiative uniquely designed to harness the potential of quantum technologies. NQM aims to harness the transformative potential of quantum technologies to drive scientific and industrial breakthroughs and create a vibrant quantum ecosystem in India. This initiative is expected to have far-reaching impacts on healthcare, finance, energy, and cybersecurity sectors, cementing India's position as global leader in quantum technologies. NQM is structured around four key verticals: quantum computing, communication, sensing and metrology, and materials and devices. Each vertical is essential for advancing research and industrial application. I would like to highlight that one of the priority of NQM is human resources development and capacity building. And in this direction, DST under the NQM has taken several proactive efforts. In record time, DST and AICTE under the National Quantum Mission have launched the world's first nationwide undergraduate quantum minor program. Our goal is to train hundreds of faculty members to effectively teach this program, positioning India as a global talent hub in quantum technologies. Through the NQM, we are committed to making India the world's leading source of quantum talent. We want our students to be the best in the world, equipped with the cutting edge knowledge and skills. To every faculty member here, by joining this FDP, you are now part of India's strategic mission. When you return to your classrooms, you will not only teach quantum concepts, you are all inspiring the next generation of leaders who build the India. Imagine a student from a small college in rural Andhra Pradesh writing code for quantum algorithm to solve public health optimization problem. Imagine a young researcher in agriculture using quantum computing to optimize crop yields by understanding weather patterns. Imagine medical students using quantum chemistry to accelerate drug discovery. This is how revolutions begin, quietly in classrooms and then loudly on the global stage. Once again, thank you very much all involved in this FDB program. Jai Hind. Thank you very much.
Thank you so much, sir. You have always been a motivation. We are in the fifth course, sir. Today we have started 1,000+ participants again in quantum communication, and great support, Dr. J.B. Reddy at the national level, and also running two call for proposals, UG quantum labs and also quantum algorithms. So a lot of research is being addressed, and thank you so much for the wonderful contribution, sir. At this time, we are happy that Professor Vineet Sahula has joined. Our director, Professor Narayan Prasad Padi, could not join because he reached only today and it is a very tight schedule. So I request Professor Sahula, who is also the Chief Investigator of Electronics and ICT Academy, which is funded by Ministry of Electronics and Information Technology, because of which we are able to offer this course at a very less rate that we are able to look at. And sir is a professor in electronics and communication engineering, and he himself is also working in quantum, and sir works on quantum PUF and various aspects. So I'll give this time to share the vision of EICT Academy and also give greetings on behalf of MNIT Jaipur.
Thank you, Dr. Pelli. It's my honor to be present here amongst all of you in the galaxy. Dr. D.V. Reddy Sahab, thank you very much at the outset for supporting our programs. And because of your support, I think we are able to reach to every corner of the country, and we are taken quite sincerely by all the participants. And we have a huge turnout, which we haven't seen for last 10 years that way. Thank you very much. Thanks, Dr. Anil Kumar Sahab and your team for giving us the opportunity to serve you. And we see that EICT Academy and MNIT are just humble facilitators to actually further the cause of spreading the quantum mission efforts. And thanks for joining us. We have a funding already from Ministry of Electronics, so we have no problem of extending our finances to your programs. And it's a very happy moment to see that more than 1,000 participants are gathered here to benefit from esteemed speakers that way. I also thank AICTE to give us a logo support for our quantum programs. And thanks to definitely to our all esteemed speakers. Some of them are present here: Dr. Mustafa, Dr. Ashwath, Dr. L. Venkat Subramaniam, and many others people. And Dr. Mani Madhukar, who has been actually the key person in motivating us and other people to actually join these efforts and carry it on that way. Just to apprise you, EICT academies are actually funded by Ministry of Electronics and IT. If phase 1 was completed during 2015 and 2023, and we had 7 academies, 3 at IITs, Kanpur, Guwahati and Roorkee, 3 at NITs, Jaipur, Warangal and Patna, and 1 at IIIT Jabalpur. We trained about more than 1 lakh participants in the phase 1. Now looking at that, Ministry has given us a very ambitious target this time also. And that's what we are putting our efforts on. And we are already on the good track that we are taken very sincerely by the participants. And we are happy to serve all of you from across the country. Thank you for joining us. I think this is all I have to say. That again, thank definitely to DST, because of which we could actually facilitate our efforts and go ahead with joining this noble cause of spreading quantum to our country people, to the benefit of country people. I just like to say one thing, that as Professor Reddy has said, quantum technology is an enabling technology by itself. Like it can be applied to any other field. The way we are applying is for random number generation and key generation for cryptography using hardware. And wherever we use conventional computing, the quantum computing is applicable. Only thing is that limited by our thought process, thinking, and the innovation we can do that way. And that's what we are going to see in this program, the application to communication. Thank you very much, and it's my honor to be here. Thank you very much.
Thank you, sir. Sir, Saula sir, we just missed acknowledging Professor K. Madhumurthy sir, who is the chairperson of AP State Council for Higher Education.
Oh,
Yeah,
I apologize. Thank you very much, sir, for
Yeah.
joining us, and we are happy to serve the faculty of Andhra Pradesh. I also like to thank our director, Professor N.P. Padi sahab, because when we first proposed to him that such thing is to be taken up, he was slightly apprehensive whether we can do it, because the quantum was the upcoming field, whether people can be interested or not. But he kept trust on us, and I think like DST and AICT, he really kept trust on us, and those efforts are now fructified, looking at a large number of participants getting benefited. Thank you very much.
Thank you, sir. Thank you, sir. At this time, another person who is also a brain behind this training programs to come through after JVB Reddy sir is Dr. L. Venkat Subramaniam. He is from IBM. He is the India quantum leader from IBM. Venkat Subramaniam sir, are you available? He is also
Yes, sir.
author of yes, sir. Yeah. Thank you, sir. He is the author of a book called Quantum Nation, and it's published widely and read, and it tells about the India's plan and India's ideas and vision behind. And a couple of months, I think in January, we interacted first. We have still not met physically, but a great admiration for sir, because he was the one who said, we have to do this. And he called it the capacity building program. And that was the vision with which he started. Dr. Mani Madhukar was my friend with IBM, University Relations, and he brought us together, and then we could meet and discuss. And then he just said, he will do like this. And can you do this for us? So I said, yes, sir, we will do it. And then we contacted Reddy sir. Reddy sir said, yes, please go ahead. We will give all the necessary support and logo support and AICT support. We will send out letters. So many things came up, and more than 1,000 participants were there in every course that we have done. All credit goes to Dr. L. Venkat Subramaniam. In one of the World Quantum Day celebrations, I still remember, I was stuck because we were trying to put the list of speakers, and we had one more day left. And Reddy sir was saying we have to celebrate very nicely and in a large scale. And Dr. L. Venkat Subramaniam put up 9 speakers within 30 minutes. They just all joined just like that. And I was amazed at the way that the great influence that he has. And because of that, the World Quantum Day was celebrated across India with more than 1,000 people celebrating that event. And a variety of thoughts were shared. Please look up MNIT, EICT Academy, and World Quantum Day on YouTube. You will get that video. You can listen to those speakers. Sridhar sir was one of them. Venkat Subramaniam sir was one of them. JB Reddy sir was one of them. So please, I would encourage all of you to go to that video. Maybe I'll post it in the link as well. So at this time, without taking much time, I will request, and he is from IBM, and he is the India leader for quantum, and he is with us. Thank you so much, sir, for joining. He's a PhD from IIT Delhi, and he has a record number of patents. I think, and that's you can look up for him, and you can read his book. I will give this time for Venkat sir to share few thoughts.
Thank you so much, sir. You are very kind. But I must say that I was amazed by the way you pulled this off. Okay, so honestly, when we met in January, I did not know what is the scale at which we can work, but the scale you took it to is has been amazing. All 4 5 courses done with hundreds of participants. But what I would really like to share in today is that in quantum, so many I've been so lucky to meet so many very 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 dedicated people like Pilli sir, like Reddy sir, like Sridhar sir, amazing people, and every time I meet a new person, it goes to a new level. And so I want to thank you for taking again the Murthy sir for taking this across Andhra Pradesh to all the colleges, to all the faculty. It's an amazing scale at which we're doing. In other countries, I many other countries also, but that which we been amazed. So thank you so much. Very exciting to be part of this, and wish you all success. And we are all with you, sir, to make sure that we achieve something great here. Thank you so much, sir.
Thank you so much, sir. At this time,
Thank you, sir.
I will request our chairperson, Professor K. Madhumurthy Garu. The book that Dr. L. Venkat Subramaniam has written has been translated into Telugu also. So at this time, I will request sir to say a few words, and maybe we can just kind of show that and express our thanks to sir.
Sir, that
Madhumurthy.
also is really thanks to Reddy sir and Sridhar sir for making the Telugu version available. So thank you so much.
I had the chance of going to part of Quantum Nation myself. It was a lucid presentation on the way quantum technologies is going to evolve. The understanding helps everything. And I recommend everybody to go to this at the beginning aspect, which creates interest and motivates you and fulfills your purpose of taking a course like this. I think it's a wonderful beginning that you can make for every one of us to go through such a. And fortunately, it's also available in our Telugu language for many of us to understand it in a much more clear manner. I think hats off to all the efforts that have been put in. I have been meeting Venkat Subramaniam Garu, J.B. Reddy Garu, Sridhar Garu. They have such sort of inspiring and motivating attitude around, which is contagious. And you get pulled into this movement. And I hope you will all feel the same very soon. So thank you for all your presence here and to bless our participants and our efforts in quantum technologies. We wish that many more youngsters are introduced to this field and make this an opportunity. Yeah. Thank you.
Thank you. Thank you very much, sir. And the book will be available on Amazon. You can look up for that in Telugu if you want to read. And the vision is that we want to make India a quantum first nation. So we must be, and we are going on the right track. If J.B. Reddy sir also agrees with me, we are on the right track, and we are doing lot of orientation, lot of awareness, and because of that, if all of us get involved, I think we'll be able to do great wonders. At this time, I will request Sridhar sir, Sridhar CV from TCS. He's head of quantum technology there at TCS, and a lot of experience, and he's also one of the authors of this curriculum that was prepared. He was part of the committee, so I will request Sridhar sir to share a few thoughts.
Yeah. Thank you, sir. Thank you for giving me the opportunity. Thank you, Dr. Madhumurthy Garu, for your kind, inspirational words from Dr. Reddy, Dr. L. Subramaniam Garu. I'm fortunate to be associated with people and some of the leaders who joined today on this call. I also thank all the friends who are joining from IT, AICT, IBM, Tripartite Dartwood, and few other startups. And thank you, distinguished faculty members, for giving me the opportunity. First of all, it's a great pleasure for me to be with all of you here today. Getting together 1,000 people for scaling our capacity building initiatives is nothing short of a great mission for the country. So we've been seeing from last 2 years, there are a series of activities that are happening across the country through National Quantum Mission. And we started this initiative for capacity building, which is a very important initiative and also coming at the right. So for this, I would like to congratulate the government of Andhra Pradesh, APSI, DST, MNIT, IIT Madras, and all the partner institutions who are putting up this remarkable program possible. It's also important that we're bringing all the 1,000 people together. So that itself is a great achievement. And because all of you have signed up for this program, so which means we are actually building the next India. So I would like to narrate a few points from the TCS story and then see how do we intertwine this into your journey going forward. So let me start with what happened at TCS so that you have full view of the things that we've been battling in our earlier days. So right from the day of building a 6-qubit quantum machine by TIFR and DRDO, so TCS is one of the sponsors of this project, to the current 156-qubit machine that is going to come in Amravati soon. So we've been going through a series of changes that are happening in these technologies, and it's amazing to be part of this transformation journey in this technology area. And believe me, so it is not new. It is actually a scaling up of our existing capabilities to a significantly higher levels. Like for example, our AI skills will go exponential times. Our cybersecurity will be much more safe and fast. And we are looking at some of these amazing sensing technologies and new materials that will intrigue us with our thoughts. And all these things will be covered here. So we started our program in 2020 around the announcement of Google Sycamore. So we started an incubation program with a very small team. And we're battling with lack of people. So we try to get half of our team from people who are with AA background and half of the people who are expats coming into our team. And we started the journey. So our objective was to make write best of the algorithms while there's a program going on with DRDO and TIFR for building the quantum machine. So we were building the software part of it. And then on the algorithm side, so we were just trying to learn what kind of algorithms are possible, how do we benchmark, how do we work on different kind of technologies that are there. Because so it's not just the superconducting that we'll be working with. So we'll also be working with ion traps, neutral atoms. So these are some of the things that you'll be understanding in the coming days. Right. So we're trying to explore all these things, benchmark all these activities, work with our partner ecosystem like IBM, AWS, Microsoft, etc., and all the OEMs who are making these quantum machines, and then try to build a team that is good enough to engage a customer and explain them how quantum is going to be useful to them. Right? So in the process, so we have built a lot of proof of concepts and proof of technologies, so which will enable us to understand quantum better. And we have created a series of pilots challenging ourselves because the number of qubits have gone from 7 to today what we are talking about 156 qubits. So you can simulate 20 qubits on your classical computer on your laptop itself, but going beyond that is challenging. And after 4 or 35, you'll break the operating system, and simulating beyond 50 is impossible. And now what we are getting to Amravati is 156 qubit quantum machine, which is powerful enough, and it is greater than all the power put together from the entire world. Right. So we'll be having an opportunity to work on that kind of system, and the timing is so right that we are setting up the Amravati quantum mission also, and defined very ambitious goals, and then trying to work for the goals that are mentioned in Amravati Quantum Declaration. But if you take a step back to a year, so the NQM has started the initiatives way back in January, and they have started this mission with call for proposals where it is called in a collaborative model. And today about 150 professors are engaged in this entire journey with over 17 technical groups working on ambitious goals that were set by NQM. So subsequently, the funding was also given to startups. So there are a lot of startups who are also working on this technology. So if you look at your old newspapers, you will see there are about 44 startups in the country, and today that number will be significantly higher. So, and I'm sure we will hit 4-digit in coming 1 or 2 years. Right. So, there's a lot of activity happening on that side, and globally also, because quantum is one of the most important technologies, and about 30 plus countries are working on this technology on a mission mode methods, and it is very strategic, and it's the power of it significant advantage. So it's a time that we're in very interesting times where we're embarking onto this journey and trying to create opportunities for India, and there are plenty of opportunities that will come on our way. I'll take one small example. So the Nobel Prize went to 3 scientists who have built this protein structure and the protein structure prediction problem, protein design and protein structure prediction problem. These two are AI problems, okay? And some of them have been working on this for years. And the developments have happened only in the last 10 years, and it is completely software. And now we have an opportunity to using quantum to significantly enhance these two algorithms and then create new medicines and new drugs, and all those things are possible. So with the knowledge that is available, so applying quantum, so we can enhance these things. And to do this, we also need to understand the underlying fundamentals of quantum, how to write algorithms, how do you translate a problem from classical domain, classical AI into quantum AI. All these things are required, right? So, and this is what the faculty development program will help to understand, get the foundations of translating a classical problem into quantum domain and things like that. And you'll also learn some of the foundational concepts, which are very, very intriguing, like entanglement. You will not believe that such a concept exists. So it will be difficult for us to believe with our eyes that it is too good to be true. So, so with NQM, so again, last year we started all these projects on a collaborative model. So we're trying to do everything collaboratively since then. So this FDP program is also a collaborative initiative of multiple institutes coming together, putting a program and helping all the faculty members to learn and multiply our skills and then create a multiplier effect for the future. So I'm sure. So with the things that we are going to learn in the next few days, so these things will be taken to a lot of students in the coming years. And Dr. Reddy sir has already quoted a few examples how we can create transformation. So, and this time we just don't want to be in software itself. We want to lead from the hardware side also. So we're learning much more things. And AICT and DST has come up with this quantum labs programs also, which is going to end on 24th. So these things will give us an opportunity to experiment on real machines, and with 156 qubit quantum machine that is available to us. So we have a lot of opportunity for us to experiment on a significant higher scale. And this is important because not many countries have this opportunity to experiment on these kind of machines. And we will have this opportunity to have a leapfrog status at the beginning, trying on bigger quantum computers and then embark on bigger initiatives. So in the next 20 days, this is a 40-hour program. So I wish you all a great learning. And in quantum, so a lot of times customers ask us, what will quantum give, right? So we say it will either give a quadratic speed up or exponential speed up. It's something that we always tell, right? So yeah, so I think we put the same spirit of learning. So we will get into quantum scale learning. So we'll learn exponentially fast and also build things exponentially fast, and then create a great economy for India. With this, on behalf of the TCS team, thank you for all the organizers, the DST team, APSI, MNIT team, and others were part of this program and giving us the opportunity for this momentous occasion. And wish you all the best. Thank you.
Thank you. Thank you so much, sir. At this time, if we are able to turn on our videos, we'll take a quick picture before we give time to our resource people to share few thoughts, and we'll move to the first lecture. Dr. Richa Goyal, Dr. Venkat Subramaniam. Maybe if we can focus a little bit also, Anil sir, towards Madhumurthy sir, a little bit. Yeah. Yeah, Dr. Richa ma'am. Yeah, I think she may be. Mustafizur sir, ma'am will be able to join.
Yes, sir.
मैम आ सकते क्या रिचा मैम कहीं है मे बी डिफिकल्ट ओके इट्स ओके थैंक यू सो मच या
Thank you, Pilli. Thank you.
Mustafizur sir, can you give a ring?
Yeah, sure.
Can join. Yeah, thank you so much for all the esteemed guests who have been with us, and we will have a brief sharing from Dr. Mustafizur Rahman and Dr. Richa Goel and Dr. Ashwath Babu are our resource people who will be sharing. And initial part of the program will be handled by IBM. 1 week, they will be doing all the basics. And surprisingly, here I have my good friend, Dr. Mustafizur. Many times we expect that they will do a lot of technology, but he actually does a lot of mathematics and a lot of, the explanation, statistics, which are the, the underlying content, and then so that it becomes easy for the participants to handle the difficult concepts a little later. So that's something, yeah, Richa ma'am has joined. So, sir, Sridhar sir, Reddy sir, Saula sir, once we'll have the photograph. Reddy garu, yes, Saula sir. Vinit Saula sir. Yeah, thank you. Thank you so much. Thank you. Thank you. Thank you all. Sorry, Richa ma'am. Sorry for the inconvenience. I'll request now each of you to share a few thoughts. Dr. Richa Goel, Dr. Mustafizur Rahman, and Dr. Ashwath Babu. I think Mustafizur is ready to go. So we'll thank. And I think Dr. Richa ma'am, she is an electrical engineer herself, and she is also very much helping us with the basics of electromagnetic theory, which comes. And Dr. Ashwath Babu sir will be leading the quantum communication, quantum materials, and quantum sensing part. He's held a lot. He's also writing a book for AICT for quantum computing. They also have written a book, Dr. Mustafizur and Dr. Richa. So we have all good authors here. So I think, and their content and their material will be shared with us. So in this order, Dr. Mustafizur, Dr. Richa Goel, and then Dr. Ashwath Babu, and we'll conclude. Then we'll start the first lecture by Mustafizur again.
Yeah.
Dr. Mustafizur.
Yeah, thank you, sir. I want to thank entire community, Indian ecosystem, National Quantum Mission, DST, ICT, and all the institution. So I won't talk much because I have the first session. I want to thank everyone for giving me the opportunity to teach, and maybe Dr. Risa can tell more. Yeah.
Yeah. Thank you for this opportunity, and I really congratulate the entire team organizing you for this fabulous program, and also a big welcome to all the participants for taking out time, listening to us to all patiently, because they are 2-hour lecture, and it's really difficult to stay focused and hold you tight to the whole program. But anyways, a big welcome and thanks so much. Thank you.
Thank you. Thank you so much, ma'am. Dr. Ashwath Babu.
Very good afternoon to all the eminent people who are here. So once again, I would like to congratulate AP State Council for Higher Education for coming up with this initiative after NQM. So it's a very good initiative for the faculty from the AP state government. So mainly concentrating on building the quantum expertise among AP faculty. So, like Pillai sir was doing from the past 6 months with the AICT Academy from MNIT Jaipur. So, we are hoping same action would continue, and here also the state faculty would get a lot of the benefit. Further, they pursue their research and teaching in the field of quantum computing. So, as a resource person, we put our full efforts and ensure that whatever knowledge we have would be shared across our colleague faculties from Andhra Pradesh. So with this, I would like to thank once again, sir, for giving the opportunity, and always our mentor, IL Venkateswaran is there. So with his initiative, this all came and put us all in front of you participants. So I wish all the participants happy learning in coming days. So thank you, Pili sir, once again. Over to you.
Thank you. Thank you, Dr. Ashwath. Dr. Ashwath is PhD from IIT Kanpur and is teaching in IIIT Dharwad. And he's been resource person in many of the training programs earlier. So you will enjoy, and then you'll be happy to know that he's also from Andhra Pradesh. So thank you so much, and that's a great joy. I think we are coming to the end of this time. I will request Anil Kumar, Dr. Anil Kumar sir, Principal, AP State Council for Higher Education, to say a vote of thanks.
Sir, can we launch the video, sir?
Sir, 1 minute. Yeah, yes. Yes, yes, sir. Yes, sir. 1 minute. 1 minute.
Yes.
Yes.
Yeah, just 1 minute. They are setting it up. Participants, please note that the lectures are only for 2 hours. So I know it's difficult to take it, but if we conduct 8-hour workshop for 5 days, we can complete the program by December. But learning will be almost very less. So 20 days, you can chew the content. That's the basic idea. So whenever you miss the lecture also, maybe in the evening you can go back, because the attendance will be logged, because you are watching the video again on WebEx. So hence joining WebEx through the proper channel is very important. So please note that. And at the same time, registering for Canvas, only those who take the exams on Canvas will receive the certificate. And registration on Canvas is not automatic. We have already added your names. Only those names whom we have added will be getting the certificate, and those names have been issued to us by AP State Council for Higher Education. We already crossed 1,060, and we have got some more names. We are adding them shortly, and we will give. It's a great response, and all of them are faculty members, and they are coming from multiple fields. So it's a great encouragement to see. And one of the things that Reddy Garu has mentioned, and also Sridhar sir has mentioned, the concept is collaboration. So you can understand AICT, DST, CDAC, IBM, TCS, all these organizations and other academicians from IISc, IIT Delhi, IIT Bombay, they came together and formulated this course. Here you see, we are so many organizations coming together and trying to run this course for you. So many speakers coming together. Please understand that across there are so many fields from where faculty are coming from. You may be surprised. Dr. Anil Kumar sir, who is from AP State Council for Agriculture, is a biology expert, but he has a lot of understanding of quantum these days. Same thing with Reddy sir. He is coming from a smart grid background, but a lot of knowledge on quantum these days. So I think we are all learning. So don't worry. We are all there to help each other. I am not an expert. Dr. Maipal is not an expert. Professor Saula is not an expert, but we are all learning. We have good teachers like Dr. Mustafizur, Dr. Ashwath, who have been working in this area for last so many years. So I wish that we all work together. Please understand this. When I say this, collaboration is the key. If we want our country to win, we have to collaborate with one another, within departments, among departments, within the institute, across institutes. Let us work together. I think the National Quantum Mission model, where they say principal institute, member institute, lead institute, this setup is basically to bring people together, and let us work together to make our country proud. I think I want to leave this thought with you before we share this video, which is prepared by AP State Council for Higher Education. Just to welcome you. We wanted to show this at the beginning, but because we were on 2 different systems, we could not do that. Hearty welcome to all of you on behalf of Professor Madhumurthy sir.
Sir, JB Reddy, I want you to launch this, please. Say launch.
Yes, sir.
Okay, sir.
Sir, you can say okay and we'll start.
Okay, sir.
Yes.
Okay.
Sir, 1 minute. You can look at the big list of organizations that are involved to bring this together for you from AP State Council for Higher Education. Yeah, this list of so many organizations which are coming together to give you this. Thank you so much. Yeah, over to Dr. Anil Kumar. Vote of thanks by Dr. Anil Kumar.
Yeah. Sir, thank you very much. I'm audible, sir.
Yes, sir.
Thank you. First of all, I thank profusely our honorable chairperson, Professor K. Madhumurthy garu, for his vision in handholding all the faculty across disciplines. Sir, it's a first of its kind in AP or maybe in India. Our chairman involved all the universities, whether it is a general university or a professional university, a technical university, agriculture university, fisheries university, medical, everything. So, as the quantum is a multi-disciplinary one, chairman also involved everything. And my big thanks to Dr. J.B. Reddy garu, being head of this ITM, for facilitating all these initiatives. Sir, if you remember me, during that day, that is the World Quantum Day, I called you and asked for your session. Because as you are very busy, you have referred two names, two important names. One is Dr. Venkat Subramanian garu, and one is Dr. C.V. Srinagar. That is the day, sir. That is the beginning of the day of this very important events. Event by event, with your support, we could be able to submit for so many using teaching labs, and with your support, we could be able to submit for algorithms also proposals. And now it is India's largest faculty development program in quantum technology. Maybe, as Dr. Shubhagar said, it may be world's largest one. So training in a single point, 1100 people is not a simple thing. I thank all the stakeholders, humanity, DST, BTM, CSS, IBM, IIT Madras, CDAC Bangalore, Hyzer, Tirupati, and IIT Tirupati, in the coming days, IIT Tirupati. All these stakeholders, and not only this, sir, we also thank startups also. Many startups are also collaborating with this. So this is the beauty of the collaboration. So when we collaborate with each other, the things will be on a mega scale. So this is the live example of having a collaborative approach. I think with the blessings of all of you, all the stakeholders, definitely we move forward under the chairman of the organization and the leadership of our chairman level. And I thank profusely, even in his absence also, Professor Narayan Prasad Padi garu for accepting our proposal for handholding exclusive AP faculty. This is an exclusive program, maybe most of its kind in India, for having a particular state. I thank you, sir, Professor Narayan Prasad Padi garu, chairman and director of MIT. I also thank Professor Vinod Sahola garu, the chief investigator, AICT Academy. I also thank Dr. L. Subramanian garu, because he has also almost become our friend, our anxious friend. Whenever we call, whether it is midnight, he will respond us. When he is during the of this launch in US, he connected for our curriculum design in the midnight. That is his passion. Thank you very much, sir. And I also thank Dr. C.V. Srinagar. We fortunately, sir, with your both Subramanian and Srinagar efforts, we could launch the hackathon at VIT today or something. Thank you very much, sir. I also thank Dr. Mustafizur Rahman Garu, the research scientist at IBM Quantum, and this Nivedita Day, which on this School of Information Technology Marketing. Also, Babu, Professor IIT Dharwad, Dr. Risha Goyal, Madam, Quantum Technical Engineer, IBM Quantum. Thank you, Madam. And Dr. Mahipal Chadesa Garu. And my special thanks to Dr. Shubhakarji, Emmanuel Shubhakarji, and his team, particularly Deepesh and others. Sir, they have worked for Saturday and Sunday also. And even there is a festival. Krishnastami is a famous festival in Jaipur. But round the clock, they have conducted the training session, how to log in, how to log in the Webex, how to log in the canvas also. They have handled all the faculty members, almost around 1,000 faculty members. And still, maybe, sir, I think by tomorrow, everybody can join this session. Thank you very much for all your energy and all your sacrifice 2 days. The biggest festival in Jaipur, they have sacrificed, especially my thanks to Emmanuel Garu, Deepesh Garu, and Mahipal Garu for having all these energies and all this commitment. And especially, my thanks to all our faculty members, esteemed faculty members. There are senior most faculty members, there are junior most faculty members, sir. There is a diversity of faculty. As I said, it is not only engineering faculty, agriculture faculty is there, science faculty is there, life sciences are there, even commerce and economics faculty. From all the disciplines, because our chairman sir has a greater vision. Because as you said, that 156 qubit computer is coming here, and along the base, there is a 8 qubit computer also coming. There are so many startups. And in this direction, I also plead you and I also request you to handhold our coming hackathon also. Because our chairman's vision is to handhold simultaneously both the faculty and all the students. There's a movement going on in the AP. So by 1/1/2026, as per our Honorable Chief Minister wishes, we have to produce at least 30 to 50,000 faculty members, trained faculty members, and also our students.
500 educators.
500 educators and at least 1,000 enthusiasts and advocates of this quantum computing. Yes. So at least 30 to 50,000 faculty, teachers, students, as per our CM Honorable CM target, activities for this year, sir. So I request all the stakeholders, particularly DST and QM head our dynamic J.V. Reddy Garu, and very dynamic Subramani Garu, and our friends Seva Garu, and MIT people, everybody, please contribute for the growth in the progress of this state and our students as well as faculty. I thank you very much for giving this wonderful opportunity for the action as well as Andhra Pradesh. Thank you, sir.
Thank you very much.
Thank you, sir. Just to introduce my team here, Deepesh ji, who is handling the thing. Mr. Ramesh, he's there. He's also will be handling. Ramesh is also from Andhra Pradesh, so he will be willing to help you. He'll be there on the group, so you can put your queries, dear participants. My PhD student is also here, Dr. Nitya Sharma. She is working on quantum machine learning. She's just started, so she will also be there, part of the group, and help us. So before we conclude, just I will request Dr. Mahipal, who is joint coordinator with me here. In the first QT-01 program also, he was the joint principal coordinator. So few words from him, we will come.
So I sincerely thank all of you, and I request all the participants to utilize this 20 days. And as Philly sir has already requested you, it's not just about learning. You should also follow back, ask questions regularly, and attendance will be shared. Along with attendance, the important thing is video lectures will be also shared. So in case if you missed some of the portions, you can revisit and learn. Good luck. Thank you.
Thank you so much. So every day slides will be shared. Every day the video recording will be posted. So you can immediately, in case you missed or you want to go through again, so you can check that out. So Canvas, you will have to log in shortly to get the slides and the video recordings. and WebEx is where the lectures are being held. Once again, I thank you so much. I think Jay Kumar Vaidya one of the resource person has joined. So, Dr. Jay, a few words from you and we'll conclude. We've just finished the vote of thanks, but because you have joined, Dr. Jay Kumar Vaidya
Hello,
is
good afternoon, sir.
good
Good
afternoon.
afternoon
Good,
to all.
almost you can say good evening now.
Good evening,
Yes.
sir.
So,
Uh,
Doctor, let me share a few words. He is a founder of Anutantra, which is a startup, and he's traveled around India teaching a lot of people on quantum, and he specializes on quantum programming, simulations, and other things. So he will be a resource person not only in this course but 2 and 3, mostly 3. He will be sharing most of the sessions. And Qiskit, he is a certified Qiskit trainer, and he is an IBM educator. So over to Jay Kumar sir to say a few words. You can turn on your camera if it's possible. Yeah, please
Thank
go
you,
ahead.
sir. Thank you. Just now I joined with the CPU, so no camera on that. So it is immense pleasure for me to join with all of you. Hopefully this also have grand success like M180 Jaipur QT series. So one request from my side. So quantum is new for all of us, including the resource person. So try to learn each and every day. So if you are feeling something sometimes hard, don't feel you are alone. The entire world will feel very hard about quantum. Okay. So every day you need to follow up. You need to work on. Wish you all the very best. Please follow each and every lecture. If you are feeling so vague, contact to the resource person. We are always at your doorstep. Thank you all. Thank you all for joining with us.
Thank you. Thank you so much. Thank you, Reddy Garu, for being there. Thank you. Thank you so much. Thank you so
Thank you
much,
so much.
Madhumurthy
Thank
sir,
you. Thank you.
giving
And
this opportunity.
Chairman Garu, Madhu sir, maybe sir,
Sir.
Kiskit maybe in Telugu. We can come up with in a Telugu language. Sridhar Saab and Venkat sir, with the help of this team, Jay Kumar Saab and all, can we translate to the Telugu language, Kiskit? They are available in the Bengali, some Hindi, and other languages, not in Telugu.
Already
Is
available,
it,
sir, but they need a
Actually,
revamp.
it is available in Telugu?
Yes, sir. Already someone is doing.
Oh, someone
yeah,
is doing.
we will
Yeah,
make it
maybe we
available.
can explore that. Okay, wonderful.
Sure, sir. Yeah, actually, sir is talking about Qiskit tutorial, which is open from IBM side, the software. So if the tutorial is available in Telugu, like how we have the Quantum Nation book by L. Venkat Subramaniam, sir, that is the thought process. So many of us can easily understand if it's in our own mother tongue. That's the thought. So hopefully we'll have it shortly. Qiskit software, easily you can understand. Of course, you have to write the code in English, but you can understand easily in Telugu, right? Ashwath sir can also help. So we are all available to help you. Thank you so much, sir, for this idea. Yes, sir. Thank you so much. Now
Thank you so
we
much.
will begin
I
our
have
first
another
lecture.
meeting. If you don't mind, I will leave this meeting
Yes,
now.
yes, sir. Yes, sir. We'll
All
all
things follow.
conclude and thank you,
Yes.
sir.
Thank you so much. Thank you.
We will all conclude and we will
Yeah.
hand over to Dr. Mustafizur Rahman to take the first lecture. Madhumurthy, sir, with your permission, we'll start the first session.
Please do. Please do, sir.
Yes.
Please.
Yes, sir.
Yeah,
Go
sir,
ahead.
I want to just take 2-3 minutes for the setup. And
Yeah, please go ahead. Yeah.
My
Yeah, we
request
will
to the
resume.
participants.
Audience can also take a break for 1-2 minutes. There is a small demonstration also, as Dr. Mustafizur was sharing with me. Dr. Richa Goyal will show something as a demonstration towards the end of the lecture. So please, maybe there'll be some 10-15 minutes extra we'll take today, even after 5:30 a little bit. So, or they'll try to accommodate somehow. So maybe the remaining things they will do later, right? So please stay tuned till 5:30 and a little bit more if if there is a requirement, right? So we'll just wait for 1 or 2 minutes. Mustafizur will come back and start the lecture. Thank you all.
So, in such a large gathering, I
Yes,
think
yes,
there
sir.
should be a facility to share all of them in the learning mode. I think sharing their own doubts for clarification would help within the group.
Right. Sir, actually, the modality is running like this, that the chat is continuously open and the speakers are also trained for answering the chats immediately. So it has been like that. In fact, we never planned it like that, but because the chats were coming and the chats continue to come, sir. And the speakers are now trained or they have oriented that style of teaching that they will ask something and they will clarify. So the teaching is immediately things are clarified. And of course, if something is off track, the teacher will say, okay, we'll discuss after that. Otherwise, they have this. So I think that's how we'll, but then, yeah, we'll give them some time towards the end, sir, to unmute and speak. We'll give that option definitely. What you are saying is for a time of interaction, right, sir? We'll do that, sir.
Interaction with the speaker as well as interaction amongst the participants themselves. You know,
yes, sir. Yes.
Even after the session.
Right, sir. Right, sir. We will open the discussion part in Canvas, sir, where people can start discussing. That is one option. WhatsApp group also we have kept open, sir. And as of now, today we restricted for some time, but participants were discussing and asking queries and asking questions. So also, if there is some discussion questions, we'll post it to the resource people and they can respond back during the lecture time.
That would be great.
Yes, we'll do that, sir. I think, Dr. Mustafizur, are you ready?
Yes, sir.
Yeah,
Is my screen visible? Like the screen is shared, whiteboard?
Yeah. Screen is shared. It's visible, sir. Yeah, please go ahead.
Okay, thank you.
Over to you, sir.
Hello, everyone. So welcome to this course, QT-00 and QT-01. The course name is Foundation of Quantum Computing and Application. So just confirm that I am audible to everyone. If you need me louder or something, please let me know.
Sir, you are audible.
Okay.
Yeah. Voice is fine, sir. Yes.
Okay, thank you. Okay. So I divided the lecture content into 3-4 parts just to keep you attention to the course, because sir, can you mute please? Like, yeah, thanks. Yeah. So I divided the session into 2 parts, session 1 and session 2. So we'll go through the ICT syllabus very within 1 or 2 minutes, a brief overview. Some of the reference materials, because other QT like QT-01 to QT-06 in MNIT series, I was also part of the course as a speaker. So I thought let me introduce some of the reference material which will help you to get the course in your leisure time, or if you want to go deep with the subject matters. And then I divided into in the first session. So because there are people from various backgrounds, so some people may coming from the basic science like biology, physics, or chemistry. Many of the participants may come from the computation like electronics, electrical, CS, or this kind of circuit branch. Some of the people may coming from the hardware like semiconductor and things. And maybe there are people from industry. So I thought to come to a session, because it's an introduction session from the various angles to the subject. And our language from tomorrow will be mathematics to understand quantum computing and the quantum technology. So in the first session, so this is also a very different way that I am trying to take this course for this AP government course series. So in the first part, we'll focus on what computation means and why the term quantum computing and what is so different. And we'll try to connect these two things from the computation angle, no physics. And then Dr. Richa, I invited her to take some 10-15 minutes on the quantum hardware, various hardware technology, which she will give an elaboration in her sessions on Friday. Then we'll start in the second session 2 parts, roadmap from quantum physics side to quantum computing, mainly from the fundamental side. And also, there is a third way of introducing the subject from quantum technology, like what are the software stack, what are the algorithm stack, that can help the students, scholars to look in the industry, what industry is looking at or what industry is doing. So introducing the subject from various angles. So that is the objective of this lecture. So if you look at the syllabus, so the availability I had from QT-01, so QT-00 will be some more basics, fundamental required for the quantum computing. Moreover, the QT-01, if you look at, so it is focusing on mainly the quantum computing, the hardware technology for various hardware technology for quantum computing, quantum sensing, quantum communication, and there is one more module on quantum material. So basically, that might be covered in some future QT. So that will be covered. So these part, and in understanding of the quantum computing part, there are certain prerequisites. So that we'll briefly cover today. Although I understand that most of the participants are already faculty members, though they all know the physics, and also I'll try to make these things so brief as brief as possible. Coming to the reference book section, so there are good number of textbooks, first of all. Among them, those who are just very new and coming to this subject and trying to understand quantum computation, have some engineering background or science background, this book is very good for them, Quantum Computation and Quantum Information by Nelson and Chuang. And also some of the participants who are interested in quantum communication side or information theory side, so this book is very good for them. The Quantum Information Theory by Mark M. Wild. Also, those who are looking for various network applications or telecommunication applications of quantum computing and the related theories, so the 10th book is one important. Those who are very much interested in basic science, especially chemistry, so they can look into this book, the number 1, Quantum Information Science by Mario Motta and the co-authors Minetti. So these are some of the important references that you may look at. Now, so I'm skipping these things because it's already late. We have less time, so let's go directly to the lecture part. So let us try to understand. So this is for the first time I'm taking the introduction session because it's too hard, because in this QT-00 and 01 there are already esteemed speakers, and everybody has a different way of teaching and different orientation of informations, etc. So if you find something like not understood or something not interesting or interesting, please feel free to, if you have any doubt, feel free to put in the chat. I'll take care of that. So let us try to understand the quantum computing in context with the classical computation. Okay. So first of all, why do we need a computer, right? So the primary goal of computation is solving problems, right? Faster, efficiently, reliability, and skill. This is important. And some of the problems are easy, like addition of certain numbers. Some of the problems may be very intractable if you want to invert certain big matrices, or if you try to solve certain differential equations, or if you want to simulate certain molecules. So if you want to compare what is the computation power or computation time required, so if you want to add, say, 2 numbers, 4-digit numbers, so if you want to do by hands, even if you don't want to use a calculator or anything, any computer, right? So typically you need a few seconds, like 2 seconds on an average, right? But the same problem, if you want to try on a CPU computer, normal computer, ordinary computer, it takes as less as 1 microsecond or less than that. But once you go from addition, simple addition, to the multiplication problem, for example, 3x3 matrix multiplication, and you want to do by hand, it takes 2 to 3 minutes or more than that. But using a CPU, you can solve it with some few microseconds, like 100 microseconds. But if you increase the difficulty level of the problem, say 4x4 matrix inversion problem, and if you try to do by hand, now it becomes very difficult. Even if you do everything, every steps correctly, still you need few minutes, like 15 minutes for a 4x4 matrix multiplication inversions, for example. CPU takes few milliseconds. And once it becomes a 100x100 matrix multiplication, for example, say 128 plus 128 antenna transmission system, for example. So it's almost intactable. It's not possible to do by hand. You need a computer, and it takes few seconds to. So when you place a call to your friend, and your friend, your relative receives that call in few seconds, right? And that is what the computational challenge, matrix inversions, right? And there are problems. For example, simulating 10 particles, that is not possible manually. Even for a CPU, it takes few weeks. So that's why people introduce the supercomputer or HPC. And even if you use an HPC or high performance computer or supercomputer and try to simulate 100 particles, right? So that is even not possible by HPC nowadays using brute force. So for example, suppose we every day we take coffee or tea, right? And if you consider the case of coffee, so that is caffeine molecule, right? So if you see the orbital structure, so there are say 24 electrons and 50 spin orbitals considerations that needs 50 plus qubits. So what is qubits? And I'll come back every day, like today, tomorrow, and next 3-4 days to explain everything mathematically. But for now, consider this is a unit of quantum information, and you need 50 plus qubit system. So if you use classical things, so you need petabytes of classical memory, right? So even if you want to simulate this kind of molecules, so you need 2 to the power 100 complex computations, which is classically almost very, very difficult, or you can say impossible for normal CPU computers. So that's why if your computational problem is bigger, you need a bigger machine to solve that. You need a different technology to solve that. Now, let me explain a little bit more what actually computational complexity means. So typically, most of the engineering problems and science problem, if you break, there are only 3 things. One is the input X, or the cause of the problem. One is the system, and one is the observation or output you get. So typically, when you can relate something that your output or your observation Y is related with X via certain functions, and that functions explicitly you know. So that is some analytical function, say, analytical function, and you are done. Your all mathematics knowledge will be helpful here. You don't need any AI or nothing you want. But in cases, in reality, what we see, always this finding the relation between input and output might not be possible, how they are related, what the system is. Like, what do I mean by system? A system can be your brain, a system can be any linear LTI system, it can be artificial neural network, it can be large language model, whatever it is. For example, let's take an example like drug transport by RBC, red blood cells. So your drug is the input, your RBC cells and underlying all the organelles, they can form a system, biological system. And after putting the drug, what observation you see, that is the output Y, as simple as it is. If it is a wireless transmission system, you have some transmitted data, you have a receiver or your receiver user, receiving user or receiving antenna, and the receiver receives certain signal Y, and he or she does not know what is transmitted X. So you also need some knowledge or some statistics of that channel given randomness, that is A, right? So most of the engineering system you can relate. If you know the relation between X and S, mathematics, it's all everything that you need to use, just direct analytical math. If you have uncertainty about A, about X, about Y, you need the probability or the statistics that I'll cover in the next day. Similarly, in the quantum thing also, you will see quantum encoding, quantum simulation, quantum measurement, and all those steps. I'll come later on. So now, depending on, say, for example, you do not know explicit relation between X and Y. So you create examples. Okay, if I give some X, I get certain Y. So Xi and Yi. So you create many such examples and you train the system A, right? Such that if you give a new input Xk, can you predict Yk? That is what machine learning task, all the deep learning, all the large language model, all the ChatGPT works on this principle, right? So that's how things are related from your model-driven systems to your data-driven model, right? So all are related. So now, if you want to solve certain problems, if your system has input some n cross A size data, A has certain n cross n system. For example, I'm assuming it's a matrix, not a network or a graph. You can always have the way to represent your system, but a simple thing is basically your input is a vector, your system is a matrix, output is another vector. And I am taking very like homogeneous dimensions, so to avoid any conflict. Now, as your n, that is the input size or the system size, n cross n, becomes high and high, and you want to solve certain things. What was my input, or what are the feature in Y, or what are the system characteristics? So suppose, for example, if you put a drug in someone's body, the activity it will do in a particular person's can be very different to another person sitting in USA or other places, right? So that's how system behaves basically, right? So now how you define the systems once the dimensionality high. So all the algorithms you are designing, that I get an observation from some biological observations or some channel output or some other applications or control system output. What can be the system behavior, whether there is a fault in the system, or what may be my actual cause. For example, if you take some EEG signal from brains and you try to evaluate whether there is some problem in the brain at certain region, what are those X's, or what are the system, like if you define the system in certain matrix dots or matrix elements, right, accordingly. So that's why you design algorithms and try to basically understand what was X, what is Y, what is A, and various characteristics. If there is uncertainties, you put probability theory to understand or to measure the uncertainty and all. So typically, when we basically try to solve problems, we normally have various classes of complexity, and I have given some examples. For example, polynomial class problem, NP class of problems, right? NP complete problems. I forcefully added this problem, exponential time, which was not mentioned in any of the literature, but I thought it is important, especially when you try to solve quantum mechanical problem or the quantum algorithm. These are two important class of algorithms: BQP, bounded quantum polynomial problem, and QMA problem. So many people does mistakes. Okay, can I solve an NP-hard problem faster on a quantum computer? The answer might be directly no, or answer is I don't know. Okay, because there is no evidence yet that you can do a NP-hard problem solvable in a quantum computer like a polynomial. That might not be possible unless until you give a theoretical proof. But what we can see, there are certain problems which are exponential in the classical computer, exponentially hard. That means what it does mean. Basically, if you plot time versus your computational activity, say A is your computational efficiency, and this is the time. How much time you need to solve a problem, right? If you want to solve a problem with certain dimension and it takes exponential time, so that might not be a good algorithm, right? So we try to find certain quantum algorithms, and we try to see whether it is polynomial in quantum or not, or QMA in quantum or not. So these kind of things we need to look at. Okay, so basically, for example, the BQP class problem, the factoring large numbers or the source algorithm, simulating quantum chemistry problem on a quantum computer, like QMA kind of problem and all. Okay, so that means if there is a complexity, we can quantify the complexity. Which kind of complexities? Like it's a traveling salesman's problem on a network optimization problem. So which class of complexity it is? Like it is an NP-hard problem, it's a polynomial problem, or can I solve this problem faster on a quantum computer or not? The answer is always it is not, might not be possible until and unless you can prove it. Okay, so now let's try to understand the. I'll take 5 minutes to come this part. Why at all we need a quantum computer? Okay, so what is the classical computer? How it works? And something that is what is known as the Moore's law in classical computing. That is important to understand or appreciate why the different technological paradigm is at all required from the semiconductor side or the chemistry and semiconductor side. Okay. So we all know what is 0 and 1 that is taught in our school and colleges. I'm not repeating it, but what we understand is that information is physical. This 1 and 0 does not run on the air. You need a physical device to produce this 0 and 1. And there is a lot of technologies, right, involved. Like, for example, compilation technique, assembling techniques, machine code executions, various logic gate operations to perform on 0 and 1. So a lot of underlying things are there to create from voltage level to certain 1 or 0, right? So if you have a high voltage level, you say 1, for example, and low voltage level, you say 0, like 0 and 1. So how you convert this, there are a lot of technology involved there, right? So that is how you prepare 0. So if you look back how we create it, so I'll take 2-3 minutes to cover this. For example, your conductor always conducts, but your semiconductor, you can control the flow of electron and your current, so that you can actually do control mechanism to prepare 1 and 0 state using transistor, right? So especially all the semiconductor technology that we have been like learning in our electronics and computer science courses in UG till date, based on which all our classical computer and supercomputer works. Typically, they are the silicon germanium based crystals, like where you operate. And later you will see there are various different quantum technology that Dr. Richa will cover. You will see there are like aluminum, for example, where is if I show it here. So there are other, like if you look at the periodic table from this 1 to 18th, like all the columns of the periodic table. So there are elements with certain specific properties of the element. So in the quantum computing framework, for example, if you are working on the traptor thing, so you may come across molecules like say yttrium and calcium. Okay, in some cases strontium. Okay, this kind of in the ion trap technology. In the photonic, you need to understand the various chemical configurations, like what are the valence electron, what is the orbital structure and all, how you can act on that. So for example, the silicon nitride based material on the photonic chip, or the lithium niobate. Okay, material you choose for certain properties. So I am not elaborating this part. Majorana qubit or the superconducting qubit also has different kind of material that Dr. Richa will discuss. But what is also important is to understand what are the material we are choosing, or is there a best material, or can we discover certain material which is suitable for various quantum activity, like qubit with good coherence time and all, right? Less error. So these are the things that we have been taught in our schools, and I'm not repeating these things. So basically, we try to understand the hybridization process in the silicon and the germanium based crystal things, right? So we choose this kind of things because they have 4 electron, and now this is not completing the octet, so you can play with this kind of molecules, like silicon and germanium. You create doping, doping. So in pure form, it can be like, yeah, it's a pure form, it's a semiconductor, but now you can change the conductivity by doping with phosphorus and aluminum, like the the molecule, like the atoms with having 5 electrons in the valence cells, or the 3 electron in the valence cells. And to complete the 8 electron at the octet principle, so you need to know, okay, if I want to make a covalent bond, so basically it has to release 1 electron, or it has to accept 1 electron, right? And that's why we call it an acceptor, and that this is a donor. And we create certain doping material, like this kind of doping, N kind of doping, where more electrons are there, and P kind of doping, where there are more holes. That means missing of electrons are there. And that's how we invented like PN junction diode, and later on the FET, like the transistor technology, like both the BJT and FET. And FET, we have created certain like the density or the concentration of those N and P and type. And most of our present day things, like the technology works based on this MOSFET kind of technology, right? Where we have created silicon or germanium based crystals with various types of doping, and we control the flow of current. But why I am saying this example here, why it is so important in quantum, is this part, this depletion layer. Because if you want to flow the current from, say, this to this particular, this is your source and this is your drain, and you want to flow current from here to here by a certain biasing voltage level. So you are controlling this flow of current using this particular gate level, and there is an intermediate layer which is called the depletion layer, right? You are miniaturizing the layer over year and year, right? To basically do the miniaturization of the process, and basically increasing the capacity of the silicon based devices. I'm coming this part. So that's why this is so important. Now let's take an example, why I'm giving the example of CMOS here, this particular case, to start the quantum computing. It's basically the classical logic is the unit is 0 and 1, and we all know that, say for example, this is a basic example, CMOS inverter circuit. And I won't go detailed of this, but what simply what it does is basically you give a, say, plus 5 volt or some higher voltage level. Okay, so if you give higher voltage level, this part, the PMOS part actually cut off. There is no flow of current because of you are increasing the depletion layer, and there is no flow of current. So what effectively you get is the passing of the ground state. So that means you get 0. Now if you give the low state, low voltage state, or the 0 volt, say for example, or minus VCC, whatever you prefer, according to the circuitry, this part will be on and this part will be off, and then plus 5 volt will pass to this PMOS, and NMOS will be cut off because of the depletion with the increasing of the depletion with no current flow will be there. So that means if you give less voltage here, you are getting a high voltage here, and you are converting this logic by a certain encoding to 1 and this particular logic to 0. So that's how you create 0 and 1. So what the essence that I wish to say is that these 0 and 1 are not running on the air. You need a physical device to create all these zeros and 1, right? Similarly, on the quantum side, on the hardware side, we'll look at how to create gate 0 and gate 1, okay, using certain hardware technology through certain hardware introduction. But the difference or the major difference is almost in most of the classical computing technology, these are either TTL based or CMOS based logic. But in quantum hardware, you will see there are various technologies, whether it is superconducting, whether it is photonic, whether it is ion trap, or it is diamond NV center. Okay, so there are various technologies that Dr. Richa will discuss. So you will see you can create this gate 0 and gate 1 differently. There is not a single technology to create this 0 and 1. Now that I was talking about this depletion layer, right? And you see, if you try to miniaturize this width, right, to create like more control on the current flow within a single chip to increase the capacity. But at certain point of time, you will see that there will be quantum tunneling effect, that even if there is not a physical pass of the electrons or the holes, but still there is a transfer of energy, right? And that was a barrier of the this digital VLSI technology to progress. But in 2014 probably, so new technology came in that area as well, that is called the TFET technology, tunneling transistor technology, which acts on the quantum tunneling effect on a classical transistor. So this is not a quantum transistor, this is a classical transistor with quantum effect. Okay. Now there is something called the Moore's law that I was telling you. So once you try to miniaturize, so what Moore's law says, the number of transistors on microchip was doubling roughly 2 years. So in every 2 years, the number of transistor doubles within a specified chip, leading to an exponential increase in the computation power that we can see in our supercomputer nowadays, and correspondingly increase in the decrease in the cost, right? So the key aspects like the exponential growth, you can create like more higher capacity chips and you can run more computations. It's an economic driver. It can do the miniaturization. But the difficulty is once you have various like once you try to decrease this, like for example, within a specified region, and you have put some billions of say transistor, right? Now every transistor you have to miniaturize, and this with the depletion width between P and N junction, that will be so miniaturized that it cannot go beyond the atomic scale, right? So quantum tunneling effect will be there. Atomic wall, what will happen? Will quickly approach a fundamental limit. You cannot build a transistor smaller than an atom, right? So that is the limit. Like for example, we are right now building the chips in certain few nanometers, okay? But the atomic scale, for example, 0.1 nanometer, you cannot go beyond that. So that means we cannot increase the transistor capability so high. Now, you may be a little bit confused. Okay, what does that mean, that capacity or computation? Okay, let me give you an example so that this concept becomes clear. Now, the most powerful supercomputers in the world today, for example, the Oak Ridge machine, right? They have the exascales computing. That means 1 exaflop computation. So 1 exaflops computation is 10 to the power 18 flops, means floating operation per second. So all of you, those who are using MATLAB or Python and you measure computation time required to solve certain algorithms, you have seen how much time you have taken, right? Or vice versa, you can say in 1 second, how much computation you could do, right? So the power of present day supercomputers are 1 exaflop. That means you can sufficiently do 10 to the power 18 computations per second, which is equivalent to 2 to the power 60 computations per second in base 2, okay? Now, if I give you 100 particle simulation, for example, you take a drop of blood and there are 100 particles, I ask you, what is the dynamics of these 100 particles in 1 second? And you need 2 to the power 100 complex computations. So you cannot simply do one even on a supercomputer, right? So that's how it is so difficult So even now, if you try to miniaturize more, like even going very nearly to the like atomic size, right? So you can increase say 10 to the power 18 so to 10 to the power 21, some zettaflop, right? Or 10 to the power 24, but still you cannot simulate 100 particles or so, right? So there are problems which are harder on a classical machine due to the Moore's limit, right? So how quantum computer address this limit? So right now, in the beginning, you have got a lot of motivation like 156 qubit machines and all our Heron processor-based IBM machine, and there are other computers from other companies who are trying to build various technology-based quantum computers, right? Just to solve problems which are very hard to do on a classical computer or impossible, such as the drug discovery, cryptography, material science, optimization. So these kind of problems are there, and we'll know more in this course. So with this, I want to take some questions here. If you have any questions, feel free to put questions. And then after say 2-3 minutes, Dr. Richa will start the hardware part, and then I'll come back and again introduce the subject from quantum physics and technological aspects. Yeah, so please feel free to put questions. Yeah, there is a question, respected sir. Can you make the presentation slow? Of course, I'll be slow due to limitation of time. I thought to cover this part, but yeah, of course, the next part, the more mathematic intensive part, I'll go very slow so that you can easily track it. Any technical question or things? So there is one question. Can you explain more about flip-flops? Okay, always, I mean, it's difficult to always compare classical and quantum, but when I will cover the quantum logic, especially various quantum gates like Pauli's and all, I'll explain how this works, because classical logics typically work. So two things are there. One is the classical computing basically works on the principle called Boolean algebra, right? The sets of zeros and one, and all the logical gates operates on this, whether they are reversible gate or non-reversible gates and all. So they works on these things. But we will soon introduce linear algebra, which is the language of quantum computing, and we will represent everything in terms of vectors, which are quantum state, and then operators, say H hat, which are basically matrices. So this will be our language. These are this is the quantum states. States will be vectors basically, and operators will be matrices to represent the same computation in a different way. Okay, could you please which laptop configuration required for quantum computing? Okay, I'll take all these questions forward sometime. Why less than 0.1 nanometer is not possible? So if you go beyond, so this is 0.1 nanometer is just an example, but there is certain atomic limit. You cannot create a silicon-based device going with size is less than a size of an atom, right? So that is not possible. That is called the physical limit or the virial limit for this classical computation. Okay. Okay, but difference between classical quantum computing will come. This question will be very clear in 2-3 days. I'll share the slide to get notes on the Moore's limit again. Okay, so maybe Dr. Risha, so I'll request you to, if you kindly share, or if you want me to share your part. So
I will share. I'll see if I
Yeah.
can or not, right?
Yeah, you please share the slide and you may continue.
Yeah. 1 minute. Participants, please note that there may not be time for you to ask the question verbally, right? So please post it in the chat. It's very difficult, complex process to unmute you and mute you, right? So please post it in the chat. Maybe towards the end of the lecture only, we'll be able to give you opportunity to ask questions, if any, and that also is a long process, right? So over to Dr. Richa. Thank you, ma'am.
Is my screen visible?
Yes, ma'am.
Okay,
Make it
great.
full screen. Maybe you can make it full screen. screen.
Why is it not showing full screen? Yeah. Okay. Basically, Mustafa explained how your classical computing hardware or technology was. So in this particular very small session, I believe like there will be a complete session on quantum hardware. So I'm not here to explain the complete quantum hardware session. I mean, it is going to be injustice to the whole session. So basically, I'm just going to enumerate the different technologies and how and why they're important and why we should be looking at all those technologies. From that aspect, I'll be covering this just as a fundamental and very basic foundational kind of introduction to these technologies. So we know that, Mustafa explained, like in classical computing, what we talk about is 0 and 1 and how you have to basically realize that 0 and 1 in a classical bit, right? How what should be a 0 and what should be 1, just like in the example that he mentioned, he showed that okay, from an from a FET point of view, he said okay, plus VCC could be plus 5 VCC could be a 1 and minus 5 VCC could be a 0, or whatever you choose it to be. But here, when we talk about the essential requirements of a quantum hardware, here are the five fundamental conditions that my hardware should be able to realize. So, from any technology point of view, whenever we are realizing a science into a technology, what basically backs that technology is the hardware, right? The concept of quantum computing came as old as I believe 1950s, 1960s, when Feynman said that since nature is not classical, it is quantum. So to simulate something like nature, we need a quantum computer. So the idea did not just came out, right? So the idea was there, but what we built upon it was beyond quantum algorithms,
Richa,
beyond
sorry to stop you. Can you please make it full screen? Some of the people are asking for full screen. So in below there is presentation mode button is there.
Okay.
Yeah, now it's good.
I'm sorry. I'm
Thanks.
so sorry for that. So, yeah, the idea, I mean, we were building on quantum computing right from the from the quantum algorithm part. There were people who were working on it as a technology. And eventually, from 2000, we found that people started working on realizing quantum computer in reality. So there, when the technology actually started taking, the science actually started taking the shape of a technology. And they called it they were different technologies, and currently also there are many technologies in the market, and each of them are trying to put their point forward that okay, why my technology is the best. So the essential requirements for any physical realization of qubit are these five. That first of all, it should be able to represent the two states. By states, I mean the quantum state. Just like Mustafa explained, there has to be a ground state represented by cat 0, excited state represented by cat 1. It can be, I mean, 0 and 1 are just representations. It can be the other way around also. Now, these states, the quantum states that we mentioned, they should be able to show superposition. They should be able to entanglement. We should be able to initialize these qubits, just like we are able to initialize any bit, and then we should be able to manipulate these qubits. That means we should be able to realize quantum gates. So as I mentioned, at the present there are many competing technologies, but these are the four which are actually holding the fort for all of us. There are solid state qubits, there are trapped ion technology, there is a topological qubit system, and there is a photonic qubit system. So different companies have kind of patronized different technologies. Solid state qubit is essentially been patronized by Google, IBM, and Rigetti. Trapped ion is actually worked upon by companies like IonQ and Honeywell. Topological qubits is the brainchild of Microsoft, while photonic qubits is being explored far and wide in academics, research, and most oftenly in by Xanadu. Each technology has their own um, pros and cons. Of course, not easy to discover, not easy to explain on each of them right now, but I'm just trying to cover basic concepts on it. When we talk about the solid state qubits, these can be, split into two types: the superconducting qubits as well as the semiconducting qubits. As well, of course, the semiconducting qubits can be realized by quantum dots, by neutral atoms, or by trapped ions. I mean, I'm going to discuss superconducting qubits a bit more in detail, leaving the others not to be discussed. Essentially, the time frame is that. So, I mean, when we are talking about the ground state and excited state, what comes to mind immediately is a hydrogen atom structure, right? Now, if of all those who have studied science in up till class 12, we know how a hydrogen atom structure looks like. I mean, we have always studied particle in a well, and we saw something like this. The energy structure was something like this, and it is called a non-harmonic oscillator, AHO. The point here is that in this kind of structure, the energy difference between the successive energy levels is non-degenerate. They are different. The energy required to jump from 0 to 1 is different from the energy required by any atom or any particle to jump from 1 to 2. Sorry. So this is the energy difference that I'm talking about, this energy difference here, right? Wait, I was looking for the laser pointer. I'm sorry. Anyways. Now, how do you realize a harmonic? How do you realize an oscillator? We all have studied the LC oscillator. In an LC oscillator, what you have essentially is an inductor, and you have a capacitor, right? Now, if they're coupled like this, you will have a energy diagram. But in this case, the difference is the energy difference between the 0 and 1 state is same as energy difference between 1 and 2. And this is what we call a degenerate energy levels. Now, this is something, such kind of structure can be realized by using a simple LC oscillator. But this type of structure cannot be used as a basis for realizing a QT-00 and a QT-1 state. Why? Because for realizing a 0 and 1 state, you need to have distinct energy levels. You need to have something that can be declared as 0 and something that can be declared as 1. Right? Which means we need to have an artificial atom which has this kind of n-harmonic LC oscillator kind of structure. This is realized by something called JJ or Josephson junction circuit. And this is what is essentially used in realizing a superconducting qubits. A Josephson junction is nothing but a non-linear inductor. So when this nonlinear inductor is coupled with the capacitor, the whole system will behave like a n-harmonic oscillator, and will give you energy levels, energy diagram, something like this. Now the question arises that how to realize the superconducting qubits. Now this kind of structure, Josephson junction, what you need is currents. Yeah, you need current. In a simple LC oscillator, the current is composed of electrons, but in Josephson junction, the current is composed of something what we call as the Cooper pair. The Cooper pair is a very special type of electron pair in which two electrons which have opposite spins are coupled together in the presence of a superconductive material. Sorry. Now, the superconductive materials are such that they will show superconductivity at temperatures which are lower than a certain temperature called the critical temperature. So there is a set of properties which is realized by a superconducting properties. Now these materials should have zero resistance. They should be coherent and should have show purity. They should be compatible with the current semiconductor technology. And these superconducting materials have been classified as conventional superconductors. These are type 1, type 2, and they require temperatures, very low temperatures as low as 1.2 Kelvin or niobium working at these temperatures. The whole system in which the whole superconducting qubits is operating, where you can realize the Cooper pairs and where you can see the Josephson junction allowing the tunneling of these Cooper pairs, is operating at very, very low temperature. By very low temperature, I mean temperature of the order of millikelvin. Imagine temperatures as low as millikelvin, almost very near to absolute zero. This temperature is almost 100 times colder than the outer space. So this is a requirement of superconducting qubit based quantum computers. Sorry. This is something that I've been trying to explain, that there's an LC oscillator, and in which you have this kind of energy diagram with degenerate energy levels. What Josephson junction gives you is this part. In this, the energy is non-linear, and this non-linearity in the energy is essentially responsible for giving us a non-linear inductor, and thus an harmonic oscillator kind of behavior. So here is how a Josephson junction is formed. It consists of two superconductors. Now these materials are usually currently the two elements that are explored are aluminium as well as niobium, essentially because the critical temperatures are, as I mentioned, around 1.2 kelvins or 9.2 kelvins, and these are temperatures which actually are able to show superconductivity. So you can see that here is a Cooper pair, and this thin insulator layer allows the tunneling of these Cooper pair through this junction, and this tunneling is basically giving rise to non-linear supercurrent, and is eventually responsible for realization of our superconducting current. So this is superconducting technology essentially, and besides, as I discussed, that these are the properties that are required for superconducting materials. Besides these conventional superconductors is also this high temperature superconductors, which is composed of material like YbCO, yttrium, barium, copper oxide. Now, these are operating at a bit higher temperature, but these materials are currently not used when we are talking about development of quantum hardware. These technologies are currently used in different technologies, because these are basically suffering from noise as well as fabrication challenges. When I talk of fabrication, I mean scaling up of our quantum bits. The second technology, as I mentioned, under this was quantum dot qubits. In this case, you have electrons which are scattered over the surface, and these are coupled via quantum dots, and the inner or the information is stored either in the form of charge or in the form of spin states. And materials that essentially that we use are silicon or gallium arsenide, and these these can be used to represent a single or multi-qubit system. When I'm talking about single or multi-qubit system, I'm essentially talking about how these qubits are manipulated, whether they are single qubit gates or whether they are multi-qubit gates. Just like if I have to express an analogy with the current classical technology. So in currently classical technology, if we talk about a NOT gate, it is a single bit gate. And if I'm talking of a gate such as an AND gate or an OR gate, these are multi-qubits because they can multi-bits because they can have more than two inputs, right? Similarly, when we talk about a qubit system, we can have a single qubit system or a multi-qubit system depending upon the number of inputs that a qubit gates are. So unlike a classical system, manipulating a multi-qubit gate is quite a technology, uh, essentially because it has to be it should be able to basically be able to entangle, and this state of entanglement should be coherent. That means it should stay in that state as long as we need. Um, if I have to establish a very simple analogy, imagine you're sitting in a room and you switch on your light. Now you want, in a classical world, you don't expect that switch would automatically go off, right? In all generally, we're not talking about the supernatural phenomena here. In generally, the switch, if it's switched on, is going to stay on as long as you need. But in a quantum world, if you switch on a certain system, it may switch off, or it may flip back to its original position after a certain time. And this time limit is called the coherence time. It is essentially because this quantum state that has been mentioned as often as ket 0 or ket 1 may lose its coherence. And this term you are going to listen quite a few times in the days to come. So multi-qubit states or multi-qubit systems are difficult to manipulate, and here is where lies the importance of quantum computing: the ability to untangle, the ability to share information such that it can be retracted by multiple qubits at a time, and multiple qubits or parallel processing is possible using these kind of systems. Now, if I talk about different quantum dot based qubits, they are spin based quantum dots, they are charge based quantum dots, and they can be hybrid architecture in which we are basically integrating quantum dots with other technologies such as photonics or superconducting for better information processing. The other technology that is a neutral atom, also known as a cold atoms. This technology is essentially working at room temperature. By room temperature, I don't mean literal room temperature. By room temperature, I mean temperatures around 50 Kelvin or so. In this case, you can see that here is a simple diagrammatic presentation. Here is a lattice or matrix of electrons, and these dots here are basically laser pulses, which are basically manipulating these electrons in at these positions. So they are basically controlled or manipulated using laser pulses. And the materials that here in this case that we use are materials like rubidium, sodium, strontium, calcium, and cesium. And this is how you are basically arranging and manipulating your cold atoms. By manipulating, I means how you are doing the different gate operations: single gate operations, single qubit operations, or multi-qubit operations. The next is the trapped ions as qubits. In this case, if you use electromagnetic fields and for representation of your qubits, and the electronic states are basically for qubit representation. Of course, here the material uses aluminium, yttrium, and beryllium. In this case, each trapped ion basically represents a single qubit, and this energy, the manipulation is done using laser. And of course, single qubit gates are done by applying your laser pulses on these trapped ions. The ions are basically again storing information as spins or charges. Entanglement is done when we are using multi-qubit operations, and they are basically helping us to couple the motion of neighboring ions in this particular case. Rydberg atom is another very interesting technology. For all those who have studied chemistry, we know that when a particular quantum of energy is given to an atom or impinged on a particular atom, the electron jumps from a low energy state to higher energy state, right? From maybe ket 0 state to ket 1 state. Now, if a very high energy, the energy given is very high, then the electron can jump from very low energy to a very high energy state. And this particular state is known as a Rydberg state. And this Rydberg state is actually what is actually used here as a quantum state. So one is this quantum state, the 0 state is a ground state, and a very high energy excited state here is actually used as a Rydberg state. The advantage of Rydberg atom being used as qubit is because they are very sensitive to electromagnetic pulses, and it is therefore very highly explored in technologies such as sensing, quantum sensing. And of course, you'll have complete session on quantum sensing here. And in this particular case, because of its sensitivity to external energy source, it is explored in different arenas. And the unique properties of Rydberg atoms includes their large dipole moments, their strong interactions, and which is essentially used for performing various quantum operations. Another very interesting technology is the photonic qubits, and it is currently exploited, especially when we talk about quantum communication. Photonic qubits, photons, as we are all aware of, are quanta of light. And in this particular case, the qubit or the quantum state is either stored as a polarization, whether it is left polarized or right polarized, whether it is horizontal or vertical polarization, whether it is anti-diagonal or anti-diagonal. The next is that they can be polarized in terms, there can be energy can be stored as path. I mean, this can be one fair way of storing energy, and this can be another. Then this can be stored as 0. The path in which this photon gets split. So there can be 2 paths at a time for a photon to travel, and one path of them can be a ket0, and another path can be a ket1 state. So the path a photon takes is chosen as one of as one of the encoding scheme. Now another one is a time bin encoding. In this case, different time slots are allocated to photons. Supposedly x time, if it is taking, is chosen as ket0 state, and y time, if it is taking, is chosen as ket1. So they usually the difference in the time is chosen as a photonic qubit state. Another interesting phenomena technology is integrated photonic. This is basically you're trying to integrate the entire photonic qubit system onto a single motherboard. It comprises of all the basic fundamentals, such as it should have a source of photons, it should have a processor, it should have a measurement or a readout system. So integrated photonics in this particular case, again, this is in principle as compared to superconducting qubits, again runs at at room temperature. By room temperature, again, I mean temperatures ranging between 2 kelvins to 50 kelvins. So of course the source and readout is happening at low temperatures. Well, the interaction of photons is occurring at around 50 kelvins or so. The issue with photonics at the moment is it has a small coherence time. Besides, the interference or the entanglement of the photons as qubits is currently difficult to manipulate. Manipulation of photons as qubits and showing them as single qubit operations and multi-qubit operations is currently a challenging problem, and which is why currently it is most people are invested in integrated photonics, in particularly telecommunication field, of course data processing and quantum sensing. The other technology is a nuclear magnetic resonance. It is one of the oldest technology, and having said that, it is still in its very nascent form. It is still limited to research labs and academia. Of course, the reason is that people are finding it difficult to scale up. As by scaling up, I mean to increase the number of qubits on a single chip. Like IBM currently has a 156 qubit system. I don't think so NMR is going beyond 8 or 10 qubits. And that would also be in this particular case, qubits are encoded in the nuclear spins of certain atoms, and the nuclei that we're talking about is those of hydrogen, the carbon isotope, as well as the fluorine isotopes. In this particular case, when these are placed in a strong external magnetic field, there is a certain splitting of D at the generated energy levels taking place in the presence of magnetic field, and this splitting of or the Zeeman effect, which occurs in the presence of external magnetic field, is a very interesting phenomena and is exploited here when we talk about manipulation of these gates. And here you are using radio frequency pulses for manipulation. Another technology is the NV center base. It is, you may say, it is some kind of analogous to the doping concept. In this case, you use a diamond. You take a diamond atom, and then first you heat it at very high temperature, then you cool it, and you do it in the presence of certain gases such as nitrogen gases, and a vacancy is created. And when it is doped with external nitrogen, these nitrogen atoms are going to sit at certain positions, and these certain positions will have a certain vacancies adjoining to it, and these are basically forming your qubits. These nitrogen vacancy sitting next to each other and coupling with each other is what forms the basis of MV center based quantum computing system. And depending upon the kind of operations or the technology that you're using, they can have different colors. Also, it would depend upon which kind of laser beam you are particularly using for exciting or impinging on these or manipulating these quantum bits. The topological qubits has always been considered as a theoretical phenomena. However, Microsoft is the leader in this technology. These are called a very special name called the exotic qubits. Just to have a very simple analogy of topological qubits, these are like a normal qubit can be said as something that you've written on a sand. So if water comes or sometimes it's affected by noise, it gets washed off. However, a topological qubits, because of its nature, topological qubits can be said to be, some kind of a system that you form using certain, using the ropes and knots, tying different ropes and knots, and forming a whole network of these knots and you on a thread. Now, if this is placed again on the same seashore and it is washed by water, do you think it is going to be affected? No. Which is why this topological qubits has found a lot of interest among the entire research community because of its immunity to noise. An analogy, I mean, these are called anti-fermionic particles. Just to explain a very basic concept. So you have gloves and you have socks, right? So you know that when you wear gloves, these gloves cannot be interchanged. A right hand glove has to be worn in a right hand, but a left hand glove needs to be worn on your left hand. While on the same case, if you have socks, the socks are interchangeable. You don't have to worry which foot should go in which sock, right? So this is how you can explain the basic concept of topological qubits, sometimes explained by a particles called majorana. Majorana fermions is something which describes a topological qubit, and the orientation of these qubits is what is defining your quantum state here. The final is, as I mentioned, is a hybrid qubit system. In this, different technologies are integrated into one technology to get the best out of the both of the technologies, such as photonics has certain positive points, and superconducting qubits have certain other points. And if you can combine the positives of both superconducting and photons and try to come up with an integrated hardware, that kind of system would be known as a hybrid qubit system. And this type of technologies is currently explored quite amongst both in research and academia, as well as of course by different industry giants. So advantages, like you are basically trying to optimize your performance into specific application, and of course it is very difficult to design and complex. So with this, I conclude my session on quantum hardware. And
And thanks, Dr. Richa, for taking this session. Thanks a lot. Yeah, shall we stop for 5 minutes and come back, or like what is for the recording here? Or anyone from MNIT? Yeah.
So,
Yeah. Actually, sir, yeah, this is not being recorded for YouTube, right? So,
Okay.
So you can continue. It is being recorded for YouTube for only for today's lecture. Like
Okay.
how we used to do 1 hour lecture, that is not there. You can continue, or if you want to give 2-3 minutes break, yeah, that's fine, no problem.
Okay, sir. And what, like till how long shall I continue? Like today?
Yeah. You can go up. You can go on another 10-15 minutes. 5:30 anyway is there. You
Okay.
can. I
Extend
already
little bit,
informed
right?
participants that 10 minutes more. Right?
Okay. Thanks.
Please
Thanks a
go
lot.
ahead. You have the response from participants. Please continue, sir.
Yeah.
Yeah. Thank you. Please go ahead.
Thanks a lot. Yeah. So let me keep the chat also. Yeah, I need to keep chat and everything open so that I can be interact with the audience in this mode. Yeah, thanks. Yeah, so we prepared the things in various ways. I got a good question. So let me start from there. So although I divided the introduction into 4 parts, and one of them was the hardware part that just taken by Dr. Richa. Thanks. And somebody asked, where from shall we start quantum computing? Is it from physics? Is it from chemistry? From computation? Well, so so let me give you this example. I think it will serve the thing. So suppose you want to reach this mountain tip, and you can start your journey from here, or anywhere, right? So these are different paths how you want to understand the technology, right? So some of them can be physics, chemistry, or others way how you want to reach. And there is a flight mode to reach there also. So that is the mathematics, right? Even this is the hope, even those are coming from non-science background or even from the finance or other background, they can directly start with the mathematics part later. Once they try to ask questions like why these kind of things are happening, why entanglement and other things, so they can again go back to various subjects, like for example various mathematical subjects like Lie algebra, abstract algebra, or the underlying physics as well, like quantum physics. Quantum physics also, there are lots of branches like open quantum system, closed quantum system, quantum information theory, quantum communication. So there are lots of literature available. And initially, I talked when I was sharing the which book shall we refer. So I told like this book is good for starting with quantum chemistry, or this book is good for starting with quantum computing, and also you can revisit that part. So so anyway, we are introducing the subject from various angles just to motivate, because when you will be teaching in your colleges and the places, so you can bring which is the most suitable part for you, and you can elaborate that part, and you can bring innovations from your side to that part, and you can engage students in that quantum computing from that angle, right? So that's all. So now, as we have limited time, although so there is a good part that I was supposed to start, that introduction quantum computing from quantum physics and algebra basically. So I'm keeping this because this will take some time. I'm keeping this topic for tomorrow. And there is a 4th part because I am part of the industry. So let me cover that part prior to this, because that will take less time. Because ultimately we have to go back to the mathematical part in order to understand the algorithms and computation especially. But of course, these hardware part are very, very important. Those who are interested to do research on the quantum hardware, material science, chemistry, and other areas. So that's why we started the subject from that angle. So, okay, let me go to, yeah. So this is the 4th part to introduce the subject, especially from the software, algorithms, and the application stack, because some of the like the professors and some of the students, scholars who are here, they might be searching for jobs. They might be searching, okay, what are the various parts of this quantum technology that we are interested in? So effectively, what we learned just from the previous 2 parts, like from my part and Dr. Richa's part, is that if you want to understand the classical logic, and it is very equivalent to how you classical logic is the fundamental unit is 0 and 1. So it's basically set of 0 and 1 string, right? So suppose you want to represent hello, and there is a bit string for this corresponding message, say 100 some 01, something like that. And there are n such bit string, right? So you can process all these informations, propagate all this information, everything on the classical logic. And how we create that classical logic is you create certain voltage level, and then you control the voltage level. For example, the ground state you equivalent to 0, or the higher potential to 1, something like that. And these are real numbers basically. That's why I put R, right? 0 and 1. Now on the quantum logic side, tomorrow we'll see in detail that quantum states, or the what we say wave functions, right? That we represent the information in that way. They are represented using vectors. Okay, so since our childhood we have learned that if you want to represent any vector, right? This is, first of all, this is a complex vector quantity, say n cross 1, right? C n cross 1. It in 2 dimension it is C 2 cross 1, right? Complex 2 cross 1, complex numbers. Vectors with complex coefficients, right? Elements, complex elements. So if you have R, it's some vectors, right? So from our class 6, 7, 8 knowledge, we know that if you want to represent a vector, you need a coordinate system. Suppose this is your x-axis and this is your y-axis. Sometimes we represent the unit of x-axis by I, and this y in the y-axis it is j. And what we have seen that if it is A amount and this is the amount B, we can represent R vector as A I cap plus B j cap. This is how we learned how to represent vectors, right? And accordingly, complex numbers also, the amplitude, phase and all, I'm not repeating those basics parts, but in general, this is how we represent. Similarly, in place of X, if you put this ket0 and ket1, so these are orthonormal vectors, means dot product between this 1 and 0 will be 0. Okay. And you can represent any quantum information ket psi as in this way, that this ket psi is a quantum state, which is a vector, and that vector needs certain basis system or representation system to represent the information. So suppose this is the alpha amount and this is the beta amount. So you can write alpha amount ket0 plus beta amount ket1, like the way we used to represent any vector, right? But there are certain special property to these vectors, and we'll come back from the probability postulates or quantum postulates of these things, how to choose value of alpha and beta, what should be the limit of alpha and beta, those things. And we will represent information. So this earlier it was 0, 1, now it is ket0 and ket1. These are column vectors, 2 cross 1 column vectors. So ket1 is basically written as 0, 1, and ket0 is basically 1, 0. And if you do the dot product between these two vectors, it's simply, it is 0, right? So that means 1, 0, if you in a Cartesian coordinate system, if you see your 1, 0, 1, 0, 0, 1, say for example, 0, 1. So 0, 1 is this point, 0, 1. So sorry, this is 1, 0, right? X-axis 0, 1 amount, and Y-axis 0 amount. And here you can get your, say, 0, 1, right? So let me draw this picture much clear way. So if this is my axis system and this is suppose a circle, for example. So what is this point? This point is 1, 0, right? And 1, 0 means 1, 0 means 1, 0. That means ket0, right? And this point is what? This point is 0, 1. That is 1. Basically 0, 1 is ket1. These are just simply vectors, column vectors. Okay. So this is related with the hardware as well, like the ket1 related to the upspin, or ket0 related to the downspin, or it is the first excited state. This is related to the ground state and all, right? So this is how the quantum, these bits are like they are vectors. They are not like scalar quantities like the classical logics. And also they are related to the physical hardware, and they are basically vector quantities, right? The information is in the vector quantities. So this is the simple way to understand what qubit means. And I'll come back with much more detail tomorrow with these things. Now let us try to understand various stack in the practical quantum system. What are the various stack? Okay. So is there any question requesting to give PPTs? Yeah, PPT I already shared to Professor Pillai sir, and he will share. Somebody is asking screen is not visible. Can anyone else confirm the screen is visible or not? Yeah, thanks. Those who cannot view, please rejoin. Yeah. So if we see that what are the important stack in the quantum technology, one is the hardware technology. Okay. So hardware part where you create those information ket0 and ket1 physically, okay, using certain microwave pulses, controlling the artificial atoms and all that Dr. Richard just introduced in various quantum architecture. Then important part is normally what you do, suppose you have a 0 and you put a NOT gate, for example, and you get 1, right? This is the very simplest logic in classical thing, right? Classical NOT gate, right? Equivalently, when you have ket0 and you want ket1, tomorrow we'll see we will be using sigma x or Pauli x operator, which is a matrix of this kind, 0, 1, 1, 0. Okay. But this is a physical device, right? Physical device that you have seen in your laboratory, basic digital electronics lab or analog electronics lab. But this sigma x you cannot see like this. This is an operation. In basically this is a physical device, but this is an operation. So for example, microwave pulse you inject on an atom, artificial atom, something like that, right? So which will equivalently operate. It's like a matrix operation on a vector, something like that. Okay, we'll come back tomorrow. So there are how to control various quantum information. So there is a control software on top of the hardware. Okay. And whatever information we try to do work, our applications, classical things, problem, everything, right, on a CPU, and we try to talk with the quantum computer. So there is an application software, like for example, this Qiskit software. So Qiskit software will connect us to talk to the hardware, right? So in Google, they have Sark, right? So there are various softwares that will help us to talk to the hardware, right? And there is something called the middleware, right? So middleware, there are various languages, for example, C, Rust, and other languages, which will help us to convert the application layer information to convert into the physical layer informations. Okay, so these are various important stuff like the application, the quantum algorithm stack, various quantum language stack, compilation. So there is something called transpilation technique in our IBM system, so that how we convert the logical setting circuits or the abstract circuit to the physical hardware. That conversion part is done optimally on a compilation technique called specialized compilation technique called transpilation. Okay, etc. And of course the hardware part. Okay, so these are various stack of the quantum technology in a quantum computing thing. Similarly, when you will be working on the photonic quantum system, you will see various source of photon generator. Okay, so source of photon generator, there will be beam splitter, right? There will be beam splitter, there will be detector. These are various devices in a photonic quantum computation system. So this is the stack for the superconducting based or the ion trap and many other technologies in this framework. But for some of the technologies, the stack is quite different. Okay. Now, the present day superconducting computer, for example, this IBM 156 cryogenic chamber looks like this. So this is a picture I took using my mobile phone, Delhi last year, October. So there was the World Telecommunication this summit, and this machine replica came from IBM to India. Just it's a replica, and the actual machine will come next year. And there is a like various temperature level. At the outer layer you have room temperature, and the innermost layer you have temperature like say 15 millikelvin. Okay, so innermost layer 15 millikelvin. So the controlling say from 300 Kelvin to this kind of temperature to have the best qubit performance, best possible practical way, right? So there are various conversion, temperature conversion steps, signal amplification, filtering, and lots of circuits here there. Okay, and the control circuits. At the bottom there is a magnetic shield chamber, and within that there are quantum processors, right? So quantum processor within which actual quantum performance are done. Now if you have multiple processor, how to connect them? So there are various coupling technology to connect them. Okay, so this is an example of how real quantum computers nowadays look like. I'll come this part tomorrow. I'm just keeping this part like this physics part again. And okay, so within this chip, so there are things like, for example, this is a 5 qubit chip. So 5 qubit chip, you have 1, 2, 3, 4, 5 qubits, and within the qubit, these are basically the Josephson junctions and the superconducting capacitors. And the technology that we are using here is called the transpon-based qubit technology, superconducting qubit technology. Okay, where each qubit are basically acting as an artificial atom. So you create artificial atoms with varying energy levels. So, for example, ground state, the excited state, and all. So that Dr. Richa just shared the things. And if you can just put many such qubits on a physical hardware, so there is a basically a coupling map, how you place the qubit, how you use the qubit, and how you talk to the software using that part. Now, so we need to understand two things. One is will be the quantum information will be representing using the qubit, that the basic quantum information set. Tomorrow we'll see what are the underlying mathematics for that. And we will operate on the qubits like digital gates you apply to get various kind of digital operations, logical operations, right? Similarly, on quantum side, you will be using various quantum gates. So on hardware, basically these physical qubits are artificial atoms or the polarized photons or other different technologies like the ions, etc. And the gates are microwave pulses here. In mathematical part, qubits will look as a vector, and the gates will be looking as unitary matrices. Okay, and we'll study a lot about various unitary matrices and how they act on various qubits. They are not only single qubit; they can be entangled qubits and all, and various underlying mathematical principle on that. So this is the part I'm just skipping here. Now the algorithm stack. So the algorithm that you will be learning, or you already have seen various learning resources. For example, various books you have seen, like source algorithm for factorizations, Grover's algorithm for unstructured search, quantum phase estimation for eigenvalue estimation, HHL algorithm for linear system solving, quantum Fourier transform for various basis transformations, amplitude amplification for more probabilistic parameter estimation, various parametric estimation. So these are basically the category of fault tolerant algorithm. That means you can effectively get the result and compare with the classical things and get the scaling in a fault tolerant quantum computer, what we don't have right now, but we have a roadmap to reach the fault tolerant quantum computer in very near future, like in 2-3 years ahead. And the algorithm that actually nowadays works, that we call the near-term algorithms, for example, variational quantum eigensolver, the quantum approximate optimization algorithm, or QAOA, the variational quantum classifier VQC, quantum variational support vector machine QSPM, sample-based quantum diagnosis QT, etc. Right? And if we get time, some of the algorithms I will explain later because it needs a lot of mathematics to discuss the underlying principles. But in general, you need to understand only three parts. What we understand each classical, how our brain works, that we understand is classical, right? Now, if you want to interact with the quantum computing frameworks, you need to understand only three parts. One is called the encoding part, that your classical information, how it is converted to quantum information. That part is called quantum encoding. Once you have the encoded information, so it will have a quantum time evolution through, if it is an isolated quantum system, you can go via the Schrodinger equation. If it is an open quantum system, you can go via the Lindblad or Master equation. And you suppose basically reach to some other evolved state cube dagger, where basically probabilities of the occurrence of various basis states changes due to quantum interference, entanglement, and superpositions. Then whatever you get, again, we don't understand what it means. Then we do quantum measurement. Once you do quantum measurement, you get some classical information back, right? So three major steps are the encoding, the quantum evolution, and the measurement. And I'll focus both the simulation, encoding, and the measurement method. So measurement method will treat by probability theory. And this simulation of the operator design part will treat with the various unitary and the Hermitian matrices. And encoding part, I'll briefly cover some of the quantum machine learning effort towards encoding, like such as GG encoding or the basis encoding, amplitude encoding, etc. So with this, I'm concluding the part today because of the lack of time. We'll come back again tomorrow for various other parts. And if you have any question, please feel free to put here. So I covered the things from technological part, and Dr. Richa covered with from hardware part. We also have seen various chemistry and semiconductor side. And tomorrow I'll briefly introduce some physics postulates related that is required to understand quantum computing. And then we'll directly go to the linear algebra, that is the language of quantum computing. So with this, I conclude my session, and you are feel free to ask any question. Thanks.
Yeah, thank you so much, Dr. Mustafizur sir. Yeah, I can understand, dear participants, that the lectures are a little bit ahead of time. Yeah, the faculty are aware that the composition of people are from various fields, right? As Mustafizur sir already mentioned, that it is going to be a little difficult, right? But let us all try to take it very positively. We will slow down. Don't worry. Tomorrow onwards, it will be very basic, right? And maybe I will request Mustafizur sir also to take a little bit on what is an overview on quantum computing tomorrow. Maybe I'll request you, sir. First 1 hour, you can talk about like what we did. You can repeat tomorrow a little bit, and also give an overview of quantum in the first 1 hour. Then we'll go into the basics of mathematics and physics of quantum computing. We should have thought about it. I think there is a we can cover that. Please don't feel under any pressure. From day one, it's going to be like this. Please prepare also. The teaching is going to be slow. You can please understand that before you start QT-05, which is the first course on quantum computation, you will do QT-01, 02, 03, 04. In fact, 04 or 03 combined together. But this will give a strong basis before you. Then quantum computation will be like cakewalk. Whether you are from degree in economics or commerce or anything, there is absolutely no problem. But please be patient, right? Don't worry. Today, because of they want to also complete their content, I think Dr. Mustafizur and Dr. Richa Goel, they went a little bit fast. I can understand you. It may be also difficult for the language also, English, maybe, but I also understand because I also struggled initially to learn completely in English.
Yeah.
So, but yeah, we need to put in effort, right? We have to place that effort, and I think slowly we'll slow down a little bit, and then we have given an introduction of the basics. So don't worry.
Yeah.
Tomorrow onwards we will start, and whatever content links they will be provided by Sir. Sir will give you videos of his own lectures, which will be additional benefit for you. So he is very much committed as a teacher. I would say more as a practitioner in IBM. He's more of a teacher at heart. So and then I think Richa ma'am also will be like that.
Yeah.
So let's hope that we will have a best time ahead, right? Yeah. Any questions that you would like to answer, sir? Yeah, the materials will be shared in Canvas. All those who are able to access Canvas can download the slides from files, and the video recording they can view by clicking on the link on modules. It will be under modules, so please look at that, right?
Right.
Yeah, slowly we'll slow down from tomorrow a little bit. I think Mustafizur also understands that, and also he'll give you an overview on what is quantum computing. Then start off with the basis. Why we are doing QT-00. Also, maybe he'll give you a slight background and then start, right?
Sure.
Thank you so much, sir. Thank you for this time. Thank you all participants. Thank you for joining tomorrow. Please help all your friends, others, and try to look at that they will benefit a lot. Attendance link is not there. All those who have registered on WebEx, yeah, the attendance will be generated, and we will. You can look at your attendance in the file. How many? Whether you are attended or not is what is shown. We are actually keeping track of how many minutes you are logged in, right? If you have logged in and logged out, all those timings will be maintained. And towards the end, we are actually looking at whether you have attended 70% or at least 50% of the lectures have you been part of or not, we are checking. So all those things anyway is not very important. Please attend all the lectures either online or offline and ensure that you will complete them. The payment link will be shared in a day or two. Don't worry about money. Money is not the issue here. So please don't worry, because there are some arrangements we have to do in our portal. We will do that and share with you immediately. Only those participants whose email is there will get a link to create. The account will automatically created and sent you. Only the password will be shared with you, and you can register and pay the money, right? Thank you so much. Thank you, Mustafizur sir. Thank you, Richa ma'am. And thank you all the team at APSHE, Apshe, and we'll do that, right? Thank you so much. Happy learning, and don't worry. Please be patient, right? Don't worry, right? By the time QT-00 completes, you'll be very comfortable. Then QT-01 starts. Then that is where quantum technology and applications will be explained to you. So we are following the syllabus, and hence don't worry. What is quantum? This is not related to quantum. Don't think like that. These are the background for quantum, right? Thank you, ma'am. Thank you for joining. Yeah, we'll take leave now. We'll meet tomorrow at 3 o'clock.
Yeah, sure. Thanks.
And Richa ma'am's class is on electromagnetic theory for 2 hours on the
Friday.
date, I think. Yeah.
Friday.
So Friday we'll have that. Friday we'll have ma'am's lecture.
Thank you very much, sir.
Yeah, sure, sir. Thank you, sir.
Sir, thank you.
Sir,
Thank you very much.
Right. Okay, sir. We'll take a break. Right. Thank you.
Bye.
Bye.